And good early afternoon, everyone. This is Ryan Miller with North Carolina Building Performance Association, welcoming you to today's webinar. We are excited to have with us Jesse Kinsley of JRS Building Science, presenting to us on the principles and fundamentals and much more of building enclosure design and materials. He is a resident building enclosure and building science expert with JRS Building Science, and we'll be hearing from him in just a little bit. I'll be kicking things off today with a little bit of some introduction and logistics, and let folks know how they can participate in today's webinar. So we'll get to Jesse in just a couple of minutes. Before we do, again, I just want to welcome everybody and thank you to our members and sponsors for helping us to put on this webinar. This one is free, and we are recording it as well, and we'll be making this available to folks out there in the industry. It is March 31st, 2020 today, so if you're listening in later on, things are pretty strange in our industry right now with a lot of folks working from home, and we at NCBPA are very happy to be offering this type of education to our members and industry professionals, and appreciate folks like Jesse for offering their knowledge and resources to us and our pros out there to help everybody learn something and maybe get a little bit of a distraction from the day-to-day. So thank you again for those folks. So as far as today's webinar goes, we'll be keeping folks on mute for the duration. We can open up the phone line towards the end. We do that just to avoid any background noise with folks eating lunch or closing car doors or having a barking dog. The presenter is allowed to have those situations happen. So if you hear that, it's probably Jesse or maybe myself. But I'll be taking questions in the chat box and kind of monitoring that. So if you do have any questions or comments on anything that comes up during Jesse's presentation, please do put that in the chat box and go to meeting, and we'll either address it there on the fly. Jesse will be stopping every so often, or we'll maybe hold it to the end and we can have a little bit of discussion there. We do have lots of webinars coming up. This is one of our technical series coming up, and then we've got more webinars that'll be tomorrow on an introduction to structural insulated sheathing with Bo Preston of Max Life Industries. We've got waste as a resource and the built environment with Kara Green. We'll be doing that one tomorrow as well. And then on Thursday, we've got one with Nikki Kruger of Ultra Air and Santa Fe Dehumidifiers on moisture control, how that is moisture is the enemy of a healthy home. And then next week, we're actually kicking off an HVAC series. So for folks that are interested in residential HVAC fundamentals, design, installation, maintenance, things like that, we actually have those starting next week with Right Tech HVAC Training, another member company. So more will be announced here in the near future. You can always find those on our event calendar. And again, just encourage everybody to check that out. If you are not already a member company, we would encourage you, of course, please do sign up and join NCBPA, $25 a month. It's for a company, and you'll get access to all of the video recordings of every webinar that we do in our member portal available online. So that's a little bit about NCBPA and what we're up to. Workforce development, education, training is really important to us right now. And again, we're just thankful to have this opportunity. So without any further ado, I'm going to kick it over to Jesse Kinsley to offer an introduction of himself and his company and get things started. So make sure that you put those questions and comments in the chat box. And Jesse, the floor is yours.
Thank you, Ryan, and thank you everyone for coming today. Hopefully we're all doing it from a living room or our place of business in a safe way. I know, as Ryan mentioned, it is a strange time, but I couldn't be more excited to kind of get this opportunity to talk to everybody a little bit about building science. When Ryan and I first discussed putting on a webinar, thinking about putting something together for NCBPA is a real tough one. Typically, presentations that I give are to architects or to contractors, there's specifiers. They're not all, or to owners groups, they're not always to such a diverse group of people that are involved, that are as involved as NCBPA. So I've tried to take a little bit of everything from a group of our presentations and put them into this. As Ryan noted, we're going to talk about building science primarily, kind of from the fundamentals on, look at some different materials, take the opportunity to talk about some stuff that's really important to me and our kind of built environment in North Carolina with air barriers. And then also have some fun and look at some lessons learned and talk about some design decisions that I've could have made differently and also on projects could have been differently. So we're going to go through all that. Thank you again for being here. I'm going to kind of jump right in. As Ryan noted, I'm going to take some breaks kind of throughout. So please bring the questions in. I'd love this to be an open conversation and not so much me talking on one end, but I appreciate it, and I'll kind of get started in here. So as Ryan noted, team, we are going to get our directions going here. Here we go. So I'm JRS Building Science. JRS Building Science is the newest branch office of JRS Engineering. As you can see here, JRS Engineering started in Vancouver, BC, actually, during the condo crisis. If everyone's familiar with that. We've been working in the Southeast US for over 5 years. We've been working nationally and internationally for longer than that. We're excited to be down here. If you can also tell from the photos, maybe who missed picture day when we were taking all of our shots. So a little bit of me, again, let me just move my GoToMeeting out of the way. So I'm the JRS NC branch project manager. I've been an enclosure consultant, actually coming up on 4 years. I've got 10 years of experience in the construction industry, working for general contractors and working for architects. For a while when I was working in Washington State, was managing the air barrier testing and field testing. I also am a Therm 1 and proudly got my building science degree from Appalachian State. I don't know if there's any mountaineers in the group, but big fan. So taking a look where we'll go with this presentation, we're going to start out with why building science. Why are we talking about building science? Why has building science become so important in the last 10, 20 years of our design? We're going to go from there and look at kind of establish a similar understanding and kind of a basic vocabulary of what we're going to talk about throughout the presentation by covering these building science basics. Most of this is going to be a refresher for everybody in the group, but I like to go in, kind of touch on everything before we move through. Then we're going to jump right into materials. Primarily for this presentation, I'm going to talk about our WRBs, our water resistant barriers, and what we're using for those. Some different options when looking at design. A lot of this presentation is going to be tailored to the commercial side. However, there's a decent amount of it that's very applicable to the residential side, and I'd love to talk about some questions on that end as well if people have interest. Kind of stepping out of materials, we'll jump into air barriers, where we sit in code now, some design considerations to look at when trying to design an air barrier, some places we can improve. Then we're going to hop into detailing, details that I commonly see missed on jobs, again, places where we could have improvement, some fun lessons learned, and then kind of wrap it up. So I'll try to take breaks kind of at each one of these milestones and go from there. There are some learning objectives. I'll just a moment. All right. Is there anything else? We can come back
this
to.
Is Ryan. Just
why are we talking?
Quick
so
note.
Kind of hopping right in. Why building about?
Hey Jesse, it's Ryan. Just a quick note. I think we lost your audio for just a little bit there on the learning objective. So for folks on the webinar, we've got an awful lot of people using GoToWebinar nowadays. In case you may not have known that, so the audio and might give us a little bit of static as we're doing this today. We did a test run yesterday. So Jesse, if you can go over the learning objectives again real quick, that'd be helpful. Thank you.
Yeah, not a problem. So with our learning objectives, we're going to understand the fundamental functions of building enclosure as it pertains to the control of air, water vapor, and thermal or heat. We want to understand how to apply these control layers, specifically to common challenges in building design. We're going to understand the limits of common materials, what materials we can use where, as an example, and all as this pertains to the established control layers. We're going to understand the differences of some of these common materials, how they impact material performance, installation, and use, and implementing enclosure design approaches that are more likely to result in an airtight enclosure and avoid design approaches that are more likely to be leaky. If everyone's with me, we're going to hop right into why building science. So why building science, why building enclosures, and why are we talking about this now? I mean, there had to have been a problem for us to need a solution with kind of standard deduction. And so I'd like to start with where design was, where design is going, and kind of some of the issues that have come from that. So if we look at design before modernism, this is a great example of kind of pre-modernism design. We have this kind of very massive building. You can see some of the principal elements. We've got stone, masonry. Our windows are set in. We have these large sills and overhangs. Looking at these a little bit closer, it's mostly talking about our materials and how we designed our building. So the first step here is we're building with some really substantial materials that can take the effects of cyclical drying and wetting. As we know, brick can get wet and dry back out, and this was allowed to do this again and again and again over the life of this building without causing a whole lot of issue. Design, when we see here, aesthetically pleasing architectural element, it also does a lot for the performance of these windows. So over top of each one of these windows, we have almost a small roof. I like to joke that when I talk to certain architect friends of mine, I have a hard time getting maybe a 1-inch head flashing above a window on some projects. And here we're installing entire roofs over these windows. You can also see that the windows were recessed fairly deep back into the facade, which took them out of the plane where they were going to take the most water and the most wind load. As we know how our buildings work on the sides and corners. Talking about corners, when you look at cornerstone, we used our material, kind of the old adage, the cornerstone, putting it wisely. We used the strongest materials where our buildings were going to take the most load, specific to the elements. Here you can see massive stone cornerstones, and because of that, we can use some of our less expensive and less robust materials, this brick, kind of inboard of these corners. We were designing for our environment and how buildings were going to be challenged. Are some cornices that were part of the replacement of the facade on this job. And while I can't speak explicitly about what these or how these were installed, what I do like to point out is this isn't 5/8 fiber cement cladding. I mean, this isn't, wood trim. These are massive, kind of bulky materials, and we're putting these up in the expectation that they're going to last a really long time. So that's kind of one of the big takeaways here, is that we're not building with the same materials and in the same way that we were. So to modernism, so design modernism. If we look at each of these buildings, we can see some similarities. We have kind of a lot more glazing in our facade. We have this additive and subtractive architecture with the ins and outs that creates roofs and soffits and sidewall conditions that are going to kind of add complexity to our design. It's no longer a box anymore. One of the things that I think it's really important to note about this slide is each one of these buildings that you can see here, all 6, have either undergone substantial renovation to their facade and their envelope, or have been torn down because of severe envelope failure. These buildings aren't that old. So it's something to really think about when we look at where we're going. There's too many architects in the group or too many big fans of architecture, but this is Villa Savoy, a building that, as well as having challenges in World War II with its occupants, this building was challenged by some pretty substantial envelope issues. As you can see, kind of the glazing was pushed out to the front. We don't have a lot of transitions. We have a varying different materials and how these were all supposed to come together in the right way. And the French government has spent a decent amount of money getting this building kind of back up into a presentable order. It's ironic because even if you Google this building today, Villa Savoy, and look at photos of it, you can still see staining coming through, where after all these repairs, it's still kind of having some struggles with the envelope. Example of 1968 concrete, this really robust material that should have lasted a long while longer, that isn't working anymore. A project where, due to thermal expansion and the materials that were chosen for this project, windows were actually making it past their fastening and were falling out. So this building had to undergo a complete reclad to mitigate those issues. Just a common thing to think about when you try to look at the effects of what a reclad can be, and the importance of designing right the first time and constructing right the first time, because it can really be detrimental to do this to an occupied building. It's not just concrete, it's not just metal. We know having a tight envelope and having a well-designed envelope is important for wood structures as well. We're going to talk about wood quite a bit in this presentation. Here's an example of some organic growth due to some moisture issues with wood frame buildings. Also, not only it's metal, this is underneath a parking deck inside of a structure, and you can see that just how the effects that moisture had on this steel frame. Back into the wood. Apologies for the back and forth here, but back into the wood, we've got sheathing and structural framing rotting out from moisture issues. This is not only bulk moisture making it in through the cladding, but then also a lot of vapor issue that wasn't managed in this building. Vapor drive coming in and kind of being trapped at that sheathing layer. The why building science. If it's okay, I'd like to just kind of go right into the building science basics. It looks like we've got a couple comments maybe so far, and then we'll take a look at those comments and see if there's any questions or if anything we can answer from there. So, building envelope basics. Build an envelope. What is an envelope? An envelope on our building, as I'm sure we all know, is our floor, our walls, and our roof. It's what keeps the outside in, what keeps the outside out and the inside in. It separates us. This is an example of kind of universal or perfect walls all the way around. One of the things I like to point out is these transitions. How do we transition from our wall to our slab? How do we transition from our wall to our roof? It's these locations where the complexity really starts. And we'll talk about some of these kind of in detail throughout the presentation. So this understanding of our materials, when you really look at an envelope, it's kind of in common practice, and I firmly agree, the best place to start is to break it up into layers. Each layer is responsible for an element of our envelope. How does it work? How does it work within the other layers? Can one control layer handle it? Can one material be a couple control layers? And how do those control layers tie in together? One way that it was taught to me is think of our control layers as a subway map. So all the different lines and routes running together. When we deal with punched openings or fenestrations, with tying in to roof conditions, we want all those control layers to tie in together. So looking at those control layers, our first one here is our water control layer. That's our water resistant barrier, weather resistant barriers could be called. It's our building wrap, it's our fluid applied. It's what we put on the outside of the building to keep it dry. We know these materials, and we're going to get a chance to talk about them a little bit more. Then we have our air control layer. So air barriers can be managed a couple different ways. You can seal the sheathing, as you can see a little bit on the photo on the left. You can use your WRB or your water resistant barrier as your air control layer. You can also take that and do it on the inside with foams and sealants and drywall and your interior finishes. That'll work as your air barrier. And we'll look at this fairly closely when we talk about air barrier. We're fortunate to have some testing of both both assemblies, interior air barriers and exterior air barriers, and how they come out actually after going through a test. Thermal control, the insulation we're all familiar with. We know these ones. So we've got BAT, XPS, polyiso, possibly mineral wool, spray foam, either open or closed. We use this stuff everywhere, but understanding what material is right for the right situation is really important, and that kind of is the basis for all of these when we think about how to design our envelopes. Our vapor control layer, something that can sometimes get missed, but it's an easy one to manage, and I think it's really important, is how are we managing vapor in our buildings? That's interior and exterior. In North Carolina, kind of this mix, in our mixed climate, we don't have it as bad as maybe Florida, and we definitely don't have it as bad as, say, Canada, but we do have to understand how vapor is working within our building and how to handle it. It can be as simple as a PVA primer on the interior, or as complex as maybe a smart membrane product that opens and closes the vapor depending on the drive. It also can be handled with our exterior weather resistant barrier at times, depending on if we're going to be vapor open or vapor closed, depending on the building design. Last one to bring in point, and this has a lot to do with vapor drive throughout the building. So dew point is the atmospheric temperature varying according to pressure and humidity, below which water droplets begin to condense and dew conform. For all of my mechanical people, I know that was probably just singing music to ears, but I like to bring it up. We know what condensation can do in our buildings, especially if you are like me and you live in an old house in the Durham area. You can see where it goes. So we'll talk about dew point and we'll talk about vapor drive kind of throughout the detailing assemblies. So it's good to look at these control layers in action. This is that subway map that I talked about. This example is the universal wall. It's kind of been widely renowned as the perfect wall, but we know that it's not perfect for every job. We'll take a look at that. Here you can see our vapor, air, water, and thermal control layers outboard of our structure. Our structure is protected. We have a cladding on the outside. It's water shedding. I'm sure this looks really familiar to everyone on the call. What typically happens, though, is something due to schedule or cost or materials available or construction type. What we usually end up with is kind of bat insulated cavity walls. If we can get a rain screen on the outside, it's fantastic. We're going to have that everywhere we can. I highly recommend it. But we're still able to get our control layers. So here you can see our exterior in yellow. That's our weather shedding layer. We have our blue and green layer as our water control layer and our air control layer. Our thermal control layer is kind of right down the center, just outboard of the center of that bat insulation. And then we have our vapor control layer on the inside. This assembly will change depending on where you are, where you're building. North Carolina is very unique in that we range from coastal climate to mountainous region. You know, climate zone 5, climate zone 4, and how do we manage that in different areas? It's important to know where you are and how these work depending on where you're building. That's kind of my first starting point. I don't know if there's any questions yet or anything we can touch on. I'm happy to. If anyone needs to take a break, have a drink of water.
Sounds good, Jesse. This is Ryan. So just wanted to offer a quick check-in for folks. And Jesse, thanks so far for the blast off on building science here. It's always helpful to have some of those reminders, and the photos you've got are great. So yeah, just as a reminder for folks, if you do have a question or a comment, please put those in to the chat box and we'll be happy to address those there. I don't see any right now. So Jesse, I think we're in good shape and I'll turn it back over to you.
Okay, great. So like I said, we're going to talk about materials and we're going to talk about some of these WRB materials. I'd be really interested in the chat box for people to talk about what they're using, what they see on their projects. If there's any issues that people are seeing with some of these materials, I'd love to talk about them. I also have maybe a little prize opportunity. I haven't figured that. Usually if this was in person, I'd be throwing candy, but we'll start right in. So mechanically attached. mechanically attached WRBs. These are our sheet goods, our Tyvek, our Type R, our Vapro. We know these materials. The kind of main advantage about them generally is cost. They are really affordable in most cases. Speed of installation, they can go on fairly quickly. Substrate prep is really minimal. We're going over our sheathing or over what's on our wall, and we're able to kind of put these on very quickly. You can put them on in kind of inclement weather. If it's hot, cold, it's not going to make too much of a difference for you. Depending on your sealants or what else you've got going on, of course, but just the material application, it's not going to make too much of a difference. And then also moisture. So if maybe our substrate's a little moist, it's not going to be too big of an issue here. We'll be able to dry some of that out on the inside, possibly if need be, or it'll dry through if we're vapor open. These come in two different kind of permeance levels. You can get vapor open, vapor closed, and understanding what those are is important. And then understanding how we detail our mechanically attached. So one of the big downfalls of mechanically attached is it allows for lateral movement, both of air and moisture, between it and the substrate it's attached to. So when using mechanically attached, we have to think how air is going to travel not only through this, but also behind it, around it. Will it come in and out somewhere? We really need to focus on sealing this every single place that we can, because if we install this everywhere and we miss a joint or miss a lap, and we can really have a breach issue, whether that be with moisture and bulk water or with air. So the question I challenge everybody for is the photo on the right is a Tyvek commercial wrap job. If anyone can tell me just by looking at the photo what country that photo was taken in, I don't know. We'll figure out some way to give points. We move right on to fully adhered membranes. So this is kind of the next line up, and these will trend cost a little bit. However, I really want to preface that cost depends on a lot of factors. Cost depends on actual cost of the material, but as we know, speed of installation, excuse me, how is it going to work within our schedule? Are we going to have some time savings and less cost savings? Ease of installation, is it going to require a lot of accessory detailing membranes? Are there going to be compatibility issues? These are all things to think about. So one of the big differences with fully adhered, obviously, is it's fully adhered. As we talked about with mechanically attached, there isn't that opportunity for lateral movement of air and water behind it because the membrane should be fully adhered to the substrate. We want to make sure these are stuck well. It also allows for some simplicity in installation where we're not having to go through and seal all of our laps and joints in our membrane. How they apply to different substrates, as you can see kind of in this center photo, we've got frame building, we've got some concrete. This membrane's able to kind of turn on all of those. In the photo on the left, we're going down actually to the concrete foundation and then up to our framing sheathing. So fully adhered can be a good option for projects, but it also isn't the only option. As we look at our next one, there's fluids. So fluids have a lot of advantages, but then also some disadvantages when we look at how we use them. Fluids similar to fully adhered or fully adhered to the building, they go on in either a roll applied or roll or trowel grade or spray applied system. However, one of the disadvantages and things that we have to be conscious about when we use fluid applied WRBs is one, what is the material that we're using and how is it going to work with the materials around it? Are we going to have to, what compatibility do we need to check to make sure that we're not going to have compatibility issues or possibly degradation of one or many membranes? Also, what's our climate like? Are we planning on doing this in December? Are we going to be doing it at 90 degrees Fahrenheit and 100% humidity on the coast of North Carolina? Is it going to be snowy in the mountains? It's cold in Raleigh? I mean, what time of year are these going on? What's our climate going to be like, and how is that going to impact not only our installation, but then also our project schedules? That the project schedule is something an envelope consultant typically doesn't push. It's kind of my residual contractor in me that I haven't been able to get rid of yet. So there's a lot of different products on the market. Understanding how they work, what their capabilities are. Also, not just looking at, and with all of these, I really recommend to people, don't think about just the kind of the blank wall slate. I mean, a lot of these materials perform very similarly when we look at them, you know, kind of through a cross section of just a wall. Think about openings, think about tie-ins. How are they going to tie in down at grade? How are they going to tie in at the roof? What are we going to do for our penetrations? These all become important when looking at different materials. There's two more on here. Pre-coated sheathings are something that have, we joke, I guess, that they're kind of really new to the market. However, people have been sealing plywood sheathing for a lot of years and kind of just relying on that. And in some climates with minimal insulation, that's worked well. I don't recommend that to anybody. I'm just saying that the idea of sealing our joints and our sheathing is not brand new. However, integrating a weather-resistant barrier and then being able to seal those joints with either fluid or tapes, sealing our penetrations if necessary, and our fastener locations if necessary, this can really be a time saver. When the sheathing goes up and the joints are sealed, I mean, the building's done. On the commercial side, I think a lot of people are starting to see these. I know Bo's coming on tomorrow. He's going to talk about kind of our next one with insulation at it as well. But then also we see a lot of these on the residential side with the zip systems. There's some thoughts on those too. I'd be happy to talk about those offline with anybody or maybe in the comment section at the end. I think these systems can work. It's understanding how they're going to work in those same parameters. How is it going to work at our openings and our detailing? How are they going to work for our building? So lastly is RB insulation air barrier combo. We've got 3 of our control layers in one. I really hope Bo doesn't mind if I stole this photo of Max Life on it, right? But these systems can really work. They get a lot done in a quick way, and they're able to handle a lot of these control layers, but understanding some of their limitations is important. So if we're installing a vapor closed or a low permeance system on our walls, we need to understand what happens with our vapor control. How is that being managed inside of the building? Are we having to take second steps to mitigate any of those risks with these systems? But all in all, they do handle a lot. I think they're impressive. They come at a high price point, but they're handling a lot of our control layers. So compatibility a bit, and I spend a decent amount of time walking around my neighborhood in Raleigh, in Durham, but then also in Raleigh, and kind of every city I go. It's contagious, I think, for most envelope consultants, is you just take pictures of things that you see. So this is roughly, 25 lineal feet of level 1 on a project kind of near my neighborhood. And here in this photo, you can see we've got PolyGuard waterproofing. We've got DCP or Grace flashing self-adhered membrane. I think that's permabarrier, and Henry damp proofing. All 3 of these materials either in contact with each other, in close proximity to each other, handling roughly the same thing, but they all come from different manufacturers, different systems. They may require different sealants, different terminations. How are we going to make sure that all these are getting done right? Now I like to interject here that I'm not proposing kind of single source for all of our projects, although I do think there can be advantages to that. I just think it's understanding what materials doing what where and how we need to treat it. I think using different products can work very well as long as we're navigating that and managing that. Quick jump through WRB materials. It looks like I've taken up another 10 minutes of your time. If anyone has any questions so far before we jump into air barriers and where code's going.
Yeah, Jesse, this is Ryan. Good time for a pause. We do have a question from Joe Archibald. He's an architect. He asked, I would be curious to hear Jesse's take on zip and zip R sheathing for residential in the Western North Carolina area of Zone 4. So, Jesse, can you give us your either partisan or unpartisan, since we're kind of neutral in these things, take on how you see zip system being used?
Yeah, Joe, I really appreciate the question. Like I said, I went to school at Appalachian State and spent a decent amount of time working on construction projects in that market. I like zip for a couple reasons, and I think that there's ways to improve it in a couple ways. So I think that zip sheathing, kind of basic zip sheathing, not the zip R. I know that they've had a lot of work done on their tapes. I'm a big fan of liquidating joints and fastener locations. I think that any time that I can get kind of minimize my risk at reverse lapse or having issues in those locations, I try to do that. With the Zip R, I haven't used it a lot. It's my understanding, and please someone correct me in this chat if I'm wrong, that the insulation is inboard of the sheathing. And while that can work, depending on where you are and depending on what other insulation you're using, increasing the insulation inboard of our sheathing, which for the zip system is our weather control and our air control layer, can at times increase our condensation risk, especially in colder climates. So we'd want to look at how much R value we're putting inboard, how we're managing vapor control in those assemblies, and maybe if we're adding R value outside, do we have exterior insulation? I think one of the things that can be missed sometimes is, even though it's considered kind of continuous CI, it's inboard of some of those control layers. So looking at all those can be important when doing that design.
Okay, well, thank you, Jesse, for the answer there. I think that was very good to hear from you on that. So I don't see any other questions, and let's go ahead and move ahead.
Okay. So as I said, we're going to talk about air barriers a bit. This is something that I'm really passionate about. I think oh, excellent. Joe, I just saw your comment. Thank you. I'm going to hide the comments now so I don't get too distracted. Talking about air barriers and air barrier testing in particular, I just really feel that it's one of the only ways that we can get a test on the work that we do on buildings. I mean, it's so hard, other than, you know, window testing, wall testing, balancing, et cetera. But for our whole building, for our building envelope, if we don't have a test, we don't really know how well we've done in particular to air. So I'm going to talk about the components of air here. So starting out, we've got nitrogen, oxygen, argon, and then this other. And this other is where it comes into the envelope spectrum, is we've got water vapor in there. We need to understand what that water vapor is doing. I'm sure a lot of people have seen it. I believe it was old Uncle Joe who put it together, talking about how much water vapor will move through a 1 inch by 1 inch hole through our air barrier. So we can have a permeance level of whatever we want it, but if we don't have a tight air barrier, water vapor is still going to make its way through, and at times that might not be the direction we want it to go. With air, we also manage temperature. Sound travels through air. We have bulk water that can travel through air, and pollution. Right now, kind of more than ever, I know North Carolina is kind of up and down, but our air quality is certainly not improving rapidly, and wanting to keep some of that, kind of the bad stuff out and the good stuff in. But buildings have to breathe. I mentioned in the early slides that I was on the contractor side of things for a while. All of my family and really close friends still are, and so this is one of those things that at every family gathering, Thanksgiving or Christmas, one of my uncles or my dad or close friends corners me and says, "Jesse, but these buildings have to breathe." And I know this is kind of repeat to our audience's ears, but they do have to breathe. How they breathe is what's important. So we need to understand the difference between ventilation and leakage. Ventilation is controlled, it's conditioned, it's known. We know where this leakage is coming from, or this ventilation is coming from. We know how much it is, we can measure it. It makes HVAC installers and commissioners' life so much easier if we can figure this out. and it's not leakage. So leakage usually comes from the places that we don't want it to. It comes from our kind of old fussy crawl spaces or attics or maybe our garage. One example in this next photo of maybe where we wish to come from is a project that our firm was involved in not too long ago on a new construction / rehabilitation that was a firehouse. So this is a interior wall that separates the firehouse kind of truck bays or engine bays from the rest of kind of the facility. And what you see here is the bat insulation was actually acting like a filter and filtering out the diesel exhaust that was coming out of the back of these fire engines because the walls weren't designed as part of the air barrier. So thankful that there was some filter in place. However, after this, and what a lot of people were hoping would have happened before that we found this out, was that this wall would have been designed as an air barrier, so we could have kept, that diesel exhaust outside of the living spaces in our buildings. And the touching back in on the residential side, residential builders and residential installers and architects, they knock this out of the park. I mean, this is stuff that we've known on the residential side for a really long time. However, it always surprises me how much it can get missed on commercial buildings, whether it's complexity or different trades or just not as kind of tuned in, or even sometimes on the residential side where we have some of those holes. And we'll look at some of those holes later on. I like to shout out where credit's due. So before we jump into where air barrier testing could be, where our air barrier code is, I like to just start with kind of where we've come from. As I noted earlier, JRS is it's got its foundings in the Pacific Northwest, so I like to compare it to Seattle a little bit, and we'll look at that in a second. So pre-2009, residential, commercial, we had no quantitative target. There was build a building, not worrying about the air barrier. In 2009, there's no quantitative target on the commercial side, but for residential, there's a visual inspection or 5 ACH or 50 pascals. So in 2009, 11 years ago now, we were testing these residential buildings, or we were doing a visual inspection. In 2012, still no improvement on the commercial side, and residential stays the same. And then in 2018, which I've gotten ahead here a little bit, but in 2018, we've gotten a little bit of change. On our commercial side, we've got materials can be confirmed. We can use prescriptive assemblies, or we can test at 4 CFM per square foot at a 75 Pascal target. Our residential is visual inspection or 5 ACH. Now this is code. This isn't all the projects that we're working on. I know a lot of the projects for people who are involved in NCBPA are going way above code. But this is what we're required to build to, and I always think that we need to understand what that level is, because some buildings are being built to that level. Where are we headed? We've made some improvements with a lot of work from a lot of people. I really do believe that testing is going to happen for commercial buildings and will likely eventually come mandatory for residential buildings in the future. I don't know when that is, but I do think it's coming, and it's something that I want to make sure that we're prepared for. So looking at the Seattle breakdown as comparison, and again, this isn't to say that one city is so far advanced from another, but this is to just kind of show that same trend in timeline and where the advancement can look like. So in 2009, there's no quantitative target. In 2009, commercial and residential went to testing. That was kind of a big jump. 2012, commercial and residential are still testing, and residential's gotten a little tighter. This is kind of standard 5 ACH. 2015, commercial's gotten tighter. We've gone to 0.3 CFM square foot. Residential's held at 5 ACH. And then the upcoming code cycle, which has been pushed a little bit by our current circumstances, is actually going to go for a little bit tighter. So it's my understanding that they're going to go for the commercial side to 0.25 with a possible credit at 0.17. And residential might be coming down as well. I'd have to double check that. If anyone knows offhand, please put it in the comment box. So it's where we can go and what it can do. It's based on these changes that we've collected a lot of the air barrier testing data that I'm going to talk about in some of the following slides. And it's all for the effect of let's get geared up now when this testing happens. Conservation code on the commercial side. I'm not going to read this aloud. I'm sure that I would butcher it. I know everyone's most likely read this before. However, I will highlight some areas. So it's currently the thermal envelope of building shall comply with section C402.51 through C402.58, or the building shall be tested. So C402.51 highlights materials that can be used that can make up an air barrier for a building. C402.51.2 is the assemblies, and so we need to understand what those assemblies are. We take a look a little bit closer at what those are. States materials and items 1 through 16, and there's 16 of these obviously, shall be deemed to comply with this section, provided the joints are sealed and the materials are installed as an air barrier in accordance with the manufacturer's instructions. Has a plywood, which is listed as item 1, I believe, or I'm not looking at the list in front of me, but I know that it's up there. Has plywood ever come with an air barrier installation instruction manual? I mean, it's just not there. Concrete CMU. So we know that these will work as air barriers, and I'll be the first person to say that they can make some really strong air barriers, but the information's not there on the front end. We're just kind of saying this is a material you can use, seal your joints, go from there. With assemblies, there's concrete masonry, there's masonry walls constructed of clay or shale, and there's stucco, basically, or plaster. These also work as air barriers, but they don't take into consideration how they tie in at the roof, how they tie in below grade, what we're doing at fenestrations. There's just a lot that's kind of missing currently. So I touch on this here. Are there holes, no pun intended, in the air barrier code? Well, maybe a little pun. We need to trust but verify. I mean, that's something that we need to always be thinking about when we're looking at design and looking at materials. So currently, there's no requirement to confirm actual leakage rates. This has some effects. I mean, we're affecting our possible building performance, how our mechanical system's going to work, also our occupant health. We talked about pollution, and you saw this example of kind of diesel smoke coming in, or maybe garage underneath a big commercial building, or there's a lot of different effects from there. If we're not testing, we can't confirm these things, and the idea is that if we don't get a score, how will we know we did? How will we know what we've done if we can't get a grade? So there's no data on means and methods. A contractor or an architect, well, a contractor can spend a lot of time doing something, an architect can spend a lot of time designing something, but if we don't actually know if it works, then are we wasting time? Are we wasting money? What are the effects of that? There's no incentive for effective execution, and I don't mean that to say that everyone's incentive-based. However, it does feel really good to kind of look at a project and get a pat on the back, or look at a house that you've just built and say, you know, we got a really tight number for our air barrier on this. What's our incentive for that? And there's no return on investment for the owner if the air barrier is a cost add. So proposing using maybe a higher quality or a more expensive system to get that air barrier, there's really no return on investment if it's not installed well. I mean, like I mentioned when we talked about WRBs, we can install you know, the most expensive material everywhere, but if we leave a hole in it, or if we leave a bunch of holes in it, it doesn't really work. They're binary. It's 1 or 0 when it comes to air barriers, and I am a firm believer that we should be trying to test it. Does anybody have any questions about code or questions about testing? I've spent a lot of time testing these buildings, and I'd be happy to kind of talk to anybody about it before we jump into the detailing section.
Thanks, Jesse, and this is Ryan. I did put a comment in there just as you were talking about some of the changing code requirements, and so just a quick mention, and folks that are in our membership know this, but we at NCBPA, of course, are always advocating for better codes. We like to see the energy codes and envelope and enclosures and things like that, you know, go up in a responsible manner. So we try to be careful about how we do that. But we are targeting, you know, required testing for residential homes to start in maybe 2022 or 2023 here in North Carolina for new construction. And then commercial will actually be looking to do building envelope commissioning, more requirements for that. Some small changes in the mid-cycle, and then once we get to the start of 2025, which will be the next kind of big cycle for North Carolina, we'll be looking to make some more changes there on the commercial side as well. So more information on our website, or we'll be happy to handle those offline, but just wanted to offer a quick mention there. So Jesse, I don't see any other questions, so I think we can go ahead and proceed.
Great, thank you. And Ryan, I appreciate obviously the work you guys are doing, and one of the things that I need to bring up when we talk about air barriers is we found that after 2009 in Washington State, the data that was taken, it was the fact that contractors were generally installing air barriers to meet code prior to the testing. What the testing did was it allowed people to understand how tight they were, and then also if there was any outliers. So if maybe one building was an offhand or an outlier that was very leaky. And so I would like to say I think we're there as a state. I mean, I see projects going up all the time that do test, and I see some that don't. And I think that the skills are there and the execution's there. It's just confirming it. So I'm gonna hop into details here, barriers, and I think that this is so high level details specific. Recommend it for residential, but as well as commercial, is having an air barrier diagram showing on our drawings where they are. In some places it's required by code, some places it's not, but having an understanding of how our air barrier works throughout the building. In plan, it comes off as fairly straightforward, but if you look here, you can see maybe there's some our air barrier doesn't belong. So for example, in this one, we have a trash chute that runs up and down all 7 floors of this building. Maybe that's some air that we want to keep outside. How are we going to do that in this building? Level 1. So if we look at the building, we can see that there's a lot more complexity to it. I mean, the air barrier is going through floor assemblies and turning corners on balconies. It's also got parapets, and how are we going to so getting the understanding from the beginning of where it needs to be can kind of give us the tools, or at least the starting point for how we plan to detail it. That I noted, how are we going to manage that? So let's variety of projects, most of which I was involved in. And if anyone sees anything that I missed, please, like I said, add to the comment section. Here, so let me make sure I'm zoomed in. Here's the uniquely attached WRB that came down and was to terminate to a soffit that was going to be installed on the underside of this PT deck. However, at some locations, we can see that the mechanically attached didn't come down far enough. And so what was happening is we were going to have locations where we were going to have a void in our air barrier at these locations. This is untied on it. Oh, what the detail was to be, pardon me, where it came, the frame, and we had to do some changes, some corrective action to get that right. This is a draw of another presentation, but I really wanted to bring it up. So this is something that I see on the commercial side in kind of my walks around, and I've seen it in a bunch of different places. Spent a lot of time on projects with post-tension decks or pre-tension, excuse me, post-tension decks, PT slabs, taking care of our PT slabs. We can't drill at certain locations more than 1 inch in fear of hitting a tendon or a cable. We have to go back and kind of grab back all these holes. And then what you'll see sometimes, as this photo will show, is we've got our PT heads, which are very delicate, just kind of out to the weather. They're gonna take full brunt of the weather, and we don't have any protection over them. Also, this is the floor or underside of the unit above. This is going to be the temperature that it is outside. There's going to be a lot of thermal bridging through here. We talk about kind of while we're down talking about slab edge, I like talking about detailing these, insulating them, or bringing them into the envelope and managing that well. So soffits and decks. These are those again from projects, or one I actually took not too long ago, where we had some discontinuities in the WRB on the underside of our, and the photo on the left is steel pan deck and photo on the right is concrete, obviously. But with a mechanically attached system, if we don't seal it everywhere, we didn't really do a lot of good for sealing it anywhere. So making sure that we're getting that everywhere is really important. When we look at HVAC penetrations, or any penetrations really, a lot of times the thought is, okay, we've got our air barrier coming through, we've had to put a duct through it, I can seal around that duct, as you can see, kind of with the green line that goes around the HVAC. But in reality, the air barrier now comes into the building. And this is something that mechanical people have known very well, is that when we tie into these kind of mechanical systems in our ductwork in a building, all of the joints in the ductwork and all of the equipment are now part of the air barrier. So how do we manage that? Making sure that we're sealing these things kind of as a whole building and not just out on the facade or out on the sheathing as we're looking at our design. So parapets, actually, if you guys will give me just 1 second, my connection is getting a little blurred. I'm just going to make an adjustment. I apologize.
And we can play some polite hold music while we're waiting for Jesse to get something fixed there. So thanks everybody for sticking around. We're about an hour in and have some additional presentation to go. So hope that you're able to stick with us. And of course, we are recording this on video, so you'll be getting a copy hopefully this afternoon, as soon as the internet start working a little bit better than they are these days, of course, given everybody working from home. So Jesse, whenever you're ready, we'll get back started with you.
I think I'm hardwired in now. We should be okay. So parapets, reducing leakage and stack effect. Rotting parapets have been something that we've known about in construction, especially the higher up we go, looking at wood frame construction, and then even some effects in steel, how air leakage in a building, how we detail this to prevent it, and then what happens. This kind of ties them all together. This is our thermal control layer, our vapor control layer, our air control layer. How do they work at the top of the buildings in this connection? You can see here in the detail, and I think we zoom in a little bit, where what we're using to make at our parapet conditions. So transitioning through insulation types to maintain our thermal control layer, reduce some of that condensation risk, but then also taking our vapor barrier, and in this case our air barrier, and extending it through to kind of close that off from air leakage. What this does is kind of bring the condensation risk inboard and allows whatever humidity or vapors inside of the parapet to vent out to vent the top. There's a lot of different ways to do this. However, I'd just like to really drive home that sealing our parapets from air leakage and trying to bring them away from the thermal boundary, push them outboard of our thermal boundary, can really be beneficial in design. But there are other ways to do it. So we talked quickly. There are two primary roofs with commercial buildings, but then also with kind of residential, where we have low slope roofs or kind of sloped roofs. And if we're going to vent our sloped roofs or our kind of vented attics, or if we're going to have a sealed attic, which I know is something a lot of people are pushing for, which I'm a big fan of, depending on where we're at. But the data that we'll talk about here comes from the differences between the two and as they relate to commercial building. So I'll kind of quickly go and see our vapor control layer through these control layers, layer which was held with our air and vapor barrier, and then turned down the inside of the wall, transitioning to a PVA primer on the interior. Our thermal control layer worked through the wall, through the insulation. Our water control layer went up, and our air control layer actually turned underneath the parapet framing, isolating it. I have some photos of that. When we detail this same location, our vapor control layer is almost roughly in the same spot. Our air control layer has to turn in and seal to the backside of what is our air control layer at the lid with our gypsum sealing. Our thermal control layer is roughly the same, and our water control layer is roughly the same. As we noted, the way that the air control layer ties into our gypsum sealing becomes really important with these vented So the data over 8 years of testing, again, this is commercial buildings, vented, unvented, and you can see kind of the range of air leakage, with vented assemblies typically being on the far side, on the farther side of leakier, and unvented assemblies having a lot more data points on the tighter side in reference to air leakage. It seems to be pretty consistent. Now, there are other effects of this, and I would be amiss to say that, you know, sometimes it can be generalized that buildings with vented attics are sometimes lower in size, and we know that height makes a difference when we're looking at testing results. But there is some consistency in the fact that we think that unvented assemblies can be a lot tighter in terms of air barriers than vented assemblies. This is an example, and it's just one way to do it, of how that air barrier was pre-stripped underneath the parapet. Was actually the roofing manufacturer's air and vapor barrier to the wall, WRB, was stripped in underneath, and the parapet was installed inside. Do that, and we need to have a vented attic, which sometimes we do. We want to make sure that we're really isolating that space. We have to think about it not only in how we're treating our lid finish, or in most cases gypsum wallboard that goes up on the ceiling, but how are we treating all these penetrations? You can see here that we've got, so if we put our gypsum wallboard in, we still have to seal kind of these sheathing joints back to the framing. Our air barrier would have had to roll in over the framing and tie in, or we'd have to transition with maybe a spray foam product. We have to seal where our wires come through. We have to seal at party walls or double walls. And then also at can lights or penetrations that we're going to have. I mean, this can get a little tricky, and so making sure that it's all done right is really important when we're looking at how to manage that. This is the, this is a penetration slide. So this is kind of rolling into the end. We're getting close to wrapping up. I don't have too many more slides, but this is one example of kind of a oopsie on my part. If anyone sees it, you'll let me know, but I'll tell you what it is nonetheless. So when working on this project was in South Carolina. The architect and I spent a lot of time coordinating on what was going to be penetrating the roof. I mean, a roof is only as strong as how many penetrations we put through it. And so understanding how that was going to work, we spent a lot of time coordinating early on with mechanical, et cetera, and we thought that we had it all. So we have our plumbing drains, we have some mechanical curbs, and we have some pipe penetrations. So when I got out the site, after the roof had been going on, you can see the details here. This is some time. This is what the roof looked like. A whole lot more penetrations than the architect or I had expected. These electrical penetrations coming up. There's dog houses that you can kind of see in the background. In a little bit closer in the foreground, you can see fall anchors. All of these pipes coming up to support the mechanical equipment. And the reason why I bring this up is it's one, to kind of show my own fault in that, but then also I kind of feel like I have to repent. But then also just to show, like, how could we have changed this? Could we have worked closer with mechanical? Could we have understood how much mechanical was going to need to be on the roof? Could we have talked about maybe consolidating this, looked at all these different penetrations we were going to have and get a plan in place for detailing them? Would they have made changes on our membrane selection? Possibly. If we would have known how much kind of liquid we were going to have to integrate based on this roof assembly and this membrane selection, it could have. So understanding all of it is important, and I like to talk about this in penetration slides. There, people can't see that far out. So last bit here is lessons learned. Fun ones that I like to always bring up and talk to about people. So we see this everywhere as either, kind of builders, installers, architects, designers, specifiers, consultants. We see this everywhere. You just get looking at buildings. And so this is membrane bleed out that happens from using either an asphaltic membrane, or using a membrane and having it too close to the edge and not terminating it properly is something that's really easy to prevent. I think it's something that we should all think about when we look at our design. This one I'm always excited to talk about. This is through-wall flashing. It's more than just drainage. So we know that we need through-wall flashings. We know that they do allow for drainage if we have a rain screen, or even if we don't have a rain screen. They're important. A lot of times I'll get pushback on through-wall flashings at lap siding installations because we're not going to get as much movement in the lap siding. Sorry, let me back up for a second. You also, with wood framed, you need them for crush or shrinkage to help minimize the effects of that on your cladding and other fenestration and your fenestrations. And so with lap siding, I get a lot of pushback in that, hey, it's lap siding, it's going to shrink as the building shrinks. We don't need a through-wall flashing. As you can see here in the photo, while the laps of shrinkage couldn't be seen in the lap siding, they could be seen in the miters of this kind of continuous fiber cement trim that was put on. The miters were blowing out. And aesthetically, this isn't that pleasing. Water intrusion-wise, it may let some more in. It's not going to be the end of the building, or the end of the building, in my opinion. However, one effect that came out of this is where that tied in from the concrete parking garage to the frame building, and just by coincidence, where this fiber cement trim had blown out, it had failed the sealant joint between the expansion joint and the building. So this is definitely a place where some improvement needed to take place. And one of the things we could have saved was the through-wall flashing. So I like to bring it in. Execution on and off the page is really important. Designers and consultants can spend a lot of time putting down kind of the best details that they can produce, getting these systems in place. For example, this is a really clear and kind of concise detail. We've got a rain screen system behind a fiber cement cladding on the exterior. We know where our WRB is. We have fastening shown. We know what our furring is going to be made of. However, when they saw this on site, I don't imagine that they thought that they were really getting a lot of drainage. And a big fault of this is not the installer, it's the designer, the kind of consultant or the contractor side of getting this information across. So we want good drainage, we want great ventilation. I know you need attachment points, but I don't know if we need this many, as you can see in that photo. So it's one of those things that I think we can all do to kind of push, no pun intended, push the envelope on how we're talking about these things and make sure that we're keeping the education going. This is an example of, I guess, well, it's an example of a couple things. So it's titled Execution on and off the page. Here, as you can see in the photo, we have two different types of insulation. Some of it's in contact with the substrate. Some of it's filling the drainage cavity behind the brick. How really effective is this, especially when we look at what the detail was supposed to be, where we have mineral wool insulation, which is neither of these types. We have a big air gap to allow for some drainage. And I also don't see any mortar net down there. I mean, there's a couple things going on. And this was fault of a few parties, and fault's not the point. I think what the point is like we need to understand what systems we're using, and we need to be able to discuss those systems efficiently and effectively with the people who are going to be installing them. Last one, I just like to see, so we had this fluid applied membrane on this job. It was going to work everywhere for us. We weren't going to have any issues. And we had details on how to detail the electrical penetrations. This is an example of where 3 electrical penetrations got put together, and how in the heck were we going to detail this. Another one here is this one, and it was just the concepts. The materials were there, but the concepts weren't. The flashing device got installed outboard of the insulation and not tied back in to the WRB as it had been drawn and designed. So getting those points across. Now with a brief conclusion, mastering the basics of building science can elevate our buildings to create durable, resilient, and healthy structures while reducing maintenance, minimizing risk, and managing budget. It's really something that every project should have. So I really appreciate you guys' time. It's an interesting time for everyone in the industry right now. So thank you for taking some of it and spending it with us and talking about these things. If I can answer any questions, please shout out, and thank you again for your time. I hope you guys all have a good day.
Great. Thanks very much, Jesse. This is Ryan with NCBPA. I'll provide a little transition here and let folks come up with some questions in the chat box if you have them. I'd like to compliment Jesse on a great presentation, and also for not using the building envelope reference until about an hour and 15 minutes in for pushing the envelope. I love to see that come up in building envelope presentations and discussions. So good job there, Jesse. That was good. Anyways, lots of amazing technical information from Jesse and his team over at JRS Building Science. So definitely want to encourage folks to check them out as you're looking to get more information or support, consulting, product advice, things like that from him and his team. I'm sure they'd be happy to help out no matter where you are, since their company is, of course, national. So we'll check and see if there's any additional questions here in the chat box while we're kind of wrapping up. Just a quick reminder that we will be sending out a video recording of this here in the very near future. And so please be on the lookout for that, and you're welcome to share that with your company and your coworkers and other folks to help them learn about these items as well. As I mentioned at the very beginning of the webinar, NCBPA has a wealth of webinars coming out. Those are all available on our events calendar on our website at buildingnc.org. And we are in the process, as we speak, of adding these video recordings to our website so that folks can have access to those, and our members have access to all of them as well. So just checking to see if there's any other questions as people are getting ready to sign off a little bit. Jesse, just to kick it back over to you, any kind of final comments, questions? We'll make sure folks get your contact information here on email, but if you don't mind sharing that, that'd be helpful.
Yeah, for sure. My email's at the bottom of the page. It's Kinsley at JRS Building Science. I'm available all the time for the most part. I mean, this is what I do. And so I thank you guys. And I think that buildings are really, really important. There's something that outlasts us, especially being from North Carolina and being a part of kind of this building community. I think that we have such an opportunity to really show everyone what our buildings can do. So thank you again for being involved, and I hope everyone has a good rest of the week.
All right, great. Thanks, Jesse. So we'll be signing off for today's webinar. If there's any other questions or comments, please let us know in email. And just want to say thanks, everybody, very much, and get in touch as you need to, and enjoy the rest of your week.